What's up, algebros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, today we're going to take a look at least squares problems, right? Some of my favorite material in the course. So we'll start with a definition. If the matrix A is m by n and B is in vector space Rm, then a least square solution of Ax equals B is some vector x hat in vector space Rn such that the magnitude or length or norm of B minus A times x hat is less than or equal to the magnitude, length, or norm of B minus Ax. And that's for all x in vector space Rn. We have a nice theorem. The set of least square solution of Ax equals B coincides with the non-empty set of solutions of the normal equations given by A transpose times A times x equals A transpose times B. We have a nice theorem. Let A be an m by n matrix. The following statements are logically equivalent, meaning if one is true, all of them are true. If one is false, all of them are false. First, we say the equation Ax equals B has a unique least square solution for each B in vector space Rn. Second, we have the columns of A are linearly independent columns. And third, we have the matrix A transpose times A is an invertible matrix. Now, if we have these statements are true, then the least square solution x hat is given by, and I can solve for it directly, x hat is A transpose times A's inverse, so think of it like one matrix and its inverse, times A transpose B. Now, let's actually talk about this, right? I don't want to just throw these formulas at you and say, hey, there we have it, let's do it. Let's actually talk about what we're discussing here. So let's say I have some subspace here. And let's say this represents the column space of a matrix A, where A is an m by n matrix. My cats are running around here. I don't know if you can hear them in the video, but you let me know in the comment section below if you hear some meows. And let's say that we have some vector B, where B is not, as you can see, it's not in the column space of A. Let's start talking about this. Let's get to writing. So we want a solution to Ax equals B when B is not an element in the column space of A. So how can I get a solution? There's no vector x where A times x will give me B. Right? B is not in the column space of A, so there's no way for me to travel amongst A to get to this vector B. So right away, it's not solvable. We say, well, okay, so what's the next best thing? So our best approximation, remember this from last time, is vector B hat. Where B hat is the projection of vector B onto the column space of A. And let's go ahead and sort of remind ourselves how that would look. So we're saying, okay, I want a solution to Ax equals B. However, there is no vector x where A times x will give me B because B is not in the column space of A. What's the best I can do, though? I don't want to say no solution and then just forget about it, though that sounds maybe appealing. I want to try to give some answer. So we would say, what's the next best solution then? Well, that would be our projection. So I drop this line down here, and then I can build this vector B hat. This would be our projection. Vector B hat. And this is in the column space of A, right? I projected vector B into the column space of A, so I should be able to get to this projection vector, and that's the best that I can do, the closest that I can get. So we'll say the following. since b hat is in the column space of A, there must be some vector, I'm going to call it x hat, where A times x hat is equal to b hat. Remember, I wanted a solution to ax equals b, but b is not in the column space of A, so really, that's not going to work. It's not going to happen, right? Sadly, that's not going to happen. However, if I'm talking about my projection, I can do that, right? There must be some vector x hat where A times x hat is equal to b hat, where b hat is the projection of b onto the column space of A. So, okay, so I can do this. Something I want you to notice, though. This pink dotted line that I have here, let me just call this something. I'm going to call it, usually we call it z, so I'm going to do that. This pink dotted line, thinking of it as a vector, is given by b minus b hat. And I want you to notice that this vector z is orthogonal to the column space of A. Orthogonal to the column space of A. I think we could use a break from the yellow. Let's switch up colors. We'll say notice that the vector z, which is equal to b minus b hat, we said, is orthogonal to the column space of A. So z lives in, or is an element of, maybe a better way to put it, z is an element of the orthogonal complement of the column space of A, which means that z equals b minus b hat is an element of we call it the left null space, but this is really the null space of A transpose. And we talked about this at the end of lecture 6.1. So if you'd like to sort of, hey, where does this come from? I don't remember we talked about this. We did. Is at the end of 6.1. So if you want to go and take a look at, we talked about dot products and inner products in that lecture. The very last example that we did went through and discussed these orthogonal complements. So something that's in the orthogonal complement to the column space of A is in the null space of A transpose, and vice versa. Those spaces as subspaces are orthogonal complements to each other. Well, okay, so then if this vector z equals b minus b hat is an element of the null space of A transpose, what does that mean? Well then, that means A transpose times b minus b hat is equal to the zero vector, right? It's the null space of A transpose, so A times, well, actually write it this way. I don't maybe want to, because that, you're looking at that, you're saying, well, that looks familiar, but maybe not quite as familiar as the following. We'll sort of take it slow. If it's an element of the null space of A transpose, that means A transpose times z is equal to the zero vector. You don't really need this step, but I think it helps make the connection a bit. Because if I'm an element of the null space of A, that means AX equals 0. If I'm an element of the null space of A transpose, that means A transpose times X equals 0. And here in particular, we're saying that Z is that element. So Z is an element of the null space of A transpose, means A transpose times Z is equal to the 0 vector. And now I can start introducing those other pieces. So we'll say, well, what did we say about this? We said Z is the same as B minus B hat. Yeah, so make that substitution in there. And then now I can actually multiply this in. I could say, well, this is the same as A transpose B minus A transpose times B hat equals the 0 vector. And here I can go ahead and add this over to the other side. So I'm going to write it this way. So then these two things must be equal if their difference is the 0 vector. So that means A transpose times B hat is equal to A transpose times B. But what did we say about B hat? Well, we said that since B hat is in the column space of A, there must be some vector x hat where A times x hat is equal to B hat. So if A times x hat is equal to B hat, then I can make that substitution here and say, well, this is the same as A transpose times A times x hat, subbing in for B hat there, is equal to A transpose times B. And these are, we have a different color so this stands out. Let's do the purple. These are the normal equations, and this is what we want to focus on for our course. We'll talk about working with inverses to solve as well, but this is really what I want to make a big deal about, the normal equations. We solve using this. And in the last little bit of space that I have, I want to show that remaining result. Let me write sort of a little note over here. If A transpose A is invertible, then A transpose A's inverse exists, and dot, dot, dot. So the idea here, the goal here, is to think about A transpose A not as a product of matrices, but imagine, what if I knew what these were? If I knew what they were, I could multiply them, and this would just be some matrix times a vector x. So think of A transpose A, say it real fast, A transpose A, A transpose A. Think of it like it's one matrix times a vector equals matrix times a vector, is what we're trying to say here. And if A transpose A is just one matrix, and I can find its inverse. I could say, okay, A transpose A's inverse, I can multiply here on the left, and then A transpose A times x hat, and then equals, and then over here on the right-hand side, I got to do the same thing. I got to multiply by that inverse on the left-hand side, and then times A transpose B. But then over here on the left, I don't have quite a ton of room to write in, but this would give me the identity times x hat. And multiplying by the identity serves as a multiplicative identity for matrices. So then solving this, so we'll say then we get x hat is equal to, I'll just scooch down here, is equal to A transpose A's inverse times A transpose B. And this gives us a direct way to solve using an inverse to find that unique solution. We're not going to focus on this so much. I really like the normal equations. I hope you like the normal equations too. It gives us an augmented system to solve, but this gives us a way to solve for x hat directly using inverses. But these are the two pieces that we have from our theorem, right? We're saying here we have the normal equations, A transpose A x, I used A x hat, but that's fine, equals A transpose B. And then here we can solve directly for x hat. A transpose A's inverse times A transpose B will be that direct solution, just like we were saying. So be comfortable with the terminology here, the normal equations, and then using inverses to solve for x directly, important for the course. And we're going to take a look at both of those ideas for some examples. So I want to find the least squares solution of ax equals b by first constructing the normal equations for x hat, solving that way, and then secondly, solving for x hat directly. So let's go ahead and let's start. So remember those normal equations, A transpose A x hat equals A transpose B. And I want to start constructing, I want to start by finding A transpose A and A transpose B. So a bit of an idea for a workflow, find A transpose A first, and then find A transpose times B. So let's show A transpose times A. So let me write matrix A first, or like leave space for it. And then A transpose is going to be here. Let me write A in first because I'm looking right at it. This is matrix A. And then if I transpose it, the columns become rows and vice versa. So this first column becomes my first row in order, -1, 2, -1. And the second column becomes my second row in order, 2, -3, 3. And I can multiply these out. You want to be thinking about sizes here. A 2 by 3 times a 3 by 2 is going to give me a 2 by 2. And let's find that 2 by 2. So here I'm going to get -1 times -1 plus 2 times 2 plus -1 times -1. So that's 1 plus 4 plus 1 gives me 6. Next I'm going to have -1 times 2 plus 2 times -3 plus -1 times 3. So that's -2 minus 6 minus 3. So -8 minus 3 is going to give me -11, it looks like. Down here, filling in the second row of the product, A transpose A. 2 times -1 plus 3, -3 times 2 plus 3 times -1. So So again, that's -2 minus 6 minus 3 gives me -11. And one more left, 2 times 2 plus -3 times -3 plus 3 times 3. So that's 4 plus 9 plus 9. 9 plus 9 gives me 18, and then 18 plus 4 gives me 22. So there we have A transpose times A. But then I want to find A transpose times B. So I have A transpose already, so I'm just going to rewrite that. And then multiplying by vector B. Vector B is this vector 4, 1, 2, and A transpose is the same as it was just a minute ago. And here we'd multiply this out. Here we have a 2 by 3 times a 3 by 1 is going to give me a 2 by 1 vector. So there's a column vector in our 2. And let's see what we get. -1 times 4 plus 2 times 1 plus -1 times 2. So -4 and then plus 2 minus 2 just leaves me with that -4. And then for that last entry, 2 times 4 plus -3 times 1 plus 3 times 2. So that's going to give me 8 minus 3 plus 6. So 6 minus 3 is going to give me 3. And then 3 plus 8 is going to give me 11. So there we have all of our stuff. Now the normal equations say, okay, A transpose A times X hat equals A transpose B. Think about this now that we can see what these parts look like just as an augmented system. Think about A transpose A as the coefficient matrix, and then augmenting with the vector A transpose B and solving as an augmented system. Right, once we start seeing what these things look like, it doesn't look so crazy anymore. But let's go ahead and show with the normal equations how we can find our solution. Yes. Yeah. Awesome. Nice. Here we go. Now I'm going to start by scaling row 2. I'm going to do a -1/11 row 2. And that's going to help out quite a bit. So row 1, I'm going to rewrite it. Row 2, if I divide everything by an 11 and flip the sign, I'm going to get 1, -2 augmented with -1. And that looks really good. And then now, this is fine to work with. Nothing crazy there. If you don't like doing arithmetic, I'd say, go slow with this. I can now bring this up, multiplying row 2 by 6. So 6 times row 2. And you'll see what I'm doing here. You could get away with a more elaborate row replacement. But you know what? I'm not trying to be a hero or anything like that. Now I'm actually going to do, so I maybe want to interchange rows at some point. I'm going to do row 1 minus row 2 in row 1's position. So let me rewrite row 2. And then here in row 1's position, got my cat's meowing at me. With his Rasputin. What's going on? You want to hang out? You want to do some least squares problems? Rasputin's being a bit of a baby right now. Let me know in the comment section below if you have cats or dogs or other pets, what kind of pets you have, if they're ever, trying to help out. Baby cat. Okay, you want to sit here? We can do some. It's tough work being a cat dad. We said we're going to do row 1 minus row 2. 6 minus 6 gives me 0. -11 minus -12. So that's -11 plus 12 gives me 1. So essentially solving for one of my entries. And then -4 minus -6, that's -4 plus 6 gives me 2. So far so good. And now I want to interchange those rows. So I'm going to write row 2 up at row 1, and row 1 down in row 2. And then I want to scale row 1 back. So I'm going to do 1/6 row 1. That's going to give me 1, -2 augmented with -1. And then I have row 2 in there. It looks like we're almost done. When we're back on campus, I should try to do a lecture while holding a cat. The entire time would be pretty cool. I'm going to replace row 1 with row 1 plus 2 times row 2. So let me rewrite row 2 first. And then in row 1's position, 1 plus 2 times 0 keeps my 1. Negative 2 plus 2 times 1 gives me that 0 that I wanted. And then in the augmented entry, negative 1 plus 2 times 2, that's negative 1 plus 4, gives me 3. And this solves for that vector x hat now. So the vector x hat is the vector with entries 3, 2. And this is how we would solve using the normal equations. What do you think about that? All right, get out of here. Now, let's talk about solving directly using the inverses, because we said also that we can build x hat by doing A transpose A's inverse times A transpose B. And what do we have for A transpose A? Remember, that was our 2 by 2 matrix. Where was it? It was here, 6, negative 11, negative 11, 22. Drop a hashtag CatDadLife in the comment section below for me. Let's find the inverse of this matrix. Inverse of a 2 by 2, not so bad. I want 1 over my determinant. My determinant is 6 times 22 minus, and then negative 11 times negative 11. So let me speed this up a bit. A negative times a negative is the same as 11 times 11, because the signs are going to cancel anyways. And that's going to be distributed into the following rearrangement of my original matrix. On the main diagonal, we swap those entries. Off the main diagonal, we negate those entries. So flip the sign. Now let me see if I can do some more work with this inverse. So A transpose A's inverse. I have 1 over, and what I can do is I can actually factor an 11 out, right? 22 has an 11, and 11 times 11 has an 11. So if I factor an 11 out, I'm left with 6 times 2, which is actually 12, minus, and I left 1 11. Yeah, rewriting that matrix. And hey, 12 minus 11 is just 1, so this is really 1 over 11. And let me just distribute that in now. So 22 divided by 11 is 2, 11 by 11 is 1 and 1, and then 6 divided by 11 does not reduce. But this is my inverse, A transpose A's inverse. Now I just have to multiply A transpose A inverse times A transpose B. So then A transpose A's inverse times A transpose B is going to give me that inverse times, what was A transpose B? That was what, negative 411, something like that. Negative 411 is what it was. And we just have to multiply this out and see what we get. So 2 times negative 4 is going to give me negative 8, plus 1 times 11 gives me 11. 1 times negative 4 gives me negative 4, plus 6 over 11 times 11 gives me 6. And if I go ahead and solve now, 11 minus 8 gives me 3. And 6 minus 4 gives me 2. And this should look familiar. I'm just solving for the same thing again. That familiar vector x hat. We did it with the normal equations, got 3, 2. We did it solving directly with inverses, got 3, 2 as well. Hey, let's see another example. So here I have matrix A to start. Let's find A transpose times A. So A transpose times A, I'll have to transpose, and then multiply by the original. The columns are 1, minus 1, 0, 2, negative 2, 2, 3, 5. Transposing, the columns become rows and vice versa. There's something that I want to point out about these matrices, because we're talking about B being outside of the column space of A and then projecting that vector into the column space of A. But I want to be clear that it's not going to be an orthogonal projection, because these columns of matrix A are not orthogonal. If I do the dot product, negative 2, minus 2, plus 0, plus 10, by inspection we can say, hey, those are not orthogonal vectors. And if I go back to this example, I didn't mention it before, but I'll mention it now. This isn't orthogonal either, right? These columns of A are not orthogonal column vectors. Negative 2, minus 6, minus 3, it's not going to give you 0. So although we were talking about projecting to make this vector B hat, and then A times X hat equals B hat, really what's happening here is we're just doing a projection with non-orthogonal vectors. So let's build this A transpose A. I want to point that out because we'll talk later about that a bit. A transpose times A. So then let's go ahead and see if we can multiply this out. Again, think about the sizes. Here I have a 2 by 4 times a 4 by 2 is going to give me a 2 by 2. Let's see what we get. So 1 times 1 plus -1 times -1 plus 0 times 0 plus 2 times 2. So 1 plus 1 plus 4 is going to give me 6. Here I'm going to get -2 plus -2 plus 0 plus 10. -2 and -2 is -4. -4 and 10 gives me 6 as well. Let's take a look at the rest. -2 times 1, 2 times -1, 3 times 0, 5 times 2. So that's another -2 minus 2 plus 10. -4 plus 10 gives me 6. And then one more entry, -2 times -2, plus 2 times 2, plus 3 times 3, plus 5 times 5. So that's going to be 4 plus 9 plus 25 should give 42, it looks like. So there's A transpose times A. But now we want to find A transpose times B. Okay, what's the worst that could happen? Here B is this vector with entries 3, 1, -4, 2. And A transpose, I can look up here to sort of cheat. And here I have a 2 by 4 times a 4 by 1. That's going to give me a 2 by 1 vector. So just a column vector in R2. What are we going to get? 1 times 3, -1 times 1, 0 times -4, 2 times 2. So that's going to give me 3 minus 1 plus 4. 3 minus 1 gives me 2. 2 plus 4 gives me 6. Another one of those hashtag #CatDadLifes down in the comment section below. We got Lily right here. She wants to do a little bit of math with us. So we get -2 times 3 for the next entry, plus 2 times 1, plus 3 times -4, plus 5 times 2. So what is that? So I have 10, and then minus 12 gives me -2, plus 2, which is now 0, plus -6. So that's just going to give me -6. Hey, so we have all of our stuff. Now I want to work with my normal equations. So I can build that augmented system. So my coefficient matrix A transpose A with rows 6, 6, and 642, and then I'm augmenting with the vector A transpose B, 6 minus 6. And we're ready to go. Now I'm going to scale the rows, of course. I'm going to do a 1/6 row 1, and I'm going to do a 1/6 row 2. Yes. So row 1, if I divide everything by 6, is going to give me 1, 1 augmented with 1. Row 2, if I divide everything by 6, is going to give me 1, 7 augmented with -1. And here we can go ahead and do our row replacement. I'm going to replace row 2 with row 2 minus row 1. So I'm going to rewrite row 1 to start, 1, 1 augmented with 1. Row 2, I'm going to get 1 minus 1 gives me 0. 7 minus 1 gives me 6. And -1 minus 1, -1 minus 1 gives me -2. Which then I'm going to go ahead and scale row 2. I'm going to do a 1/2 row 2. That's the best I can do with integers, so that's 0, 3 augmented with -1. And just for some easy arithmetic, I am going to scale up row 1. I'm going to do 3 times row 1. Do I have to do this? No. Do I want to do it? Sure. Why not? Because now I can just do some really easy subtraction. I'm not trying to impress anybody, except for maybe my cats, if you haven't noticed. I have cats. I'm going to replace row 1 with row 1 minus row 2. Let me know if you have cats in the comment section below. If you have cats, see if we can get that video, this one right here, to 500,000 likes. I get 3 minus 0 gives me 3. 3 minus 3 gives me the 0 that I wanted. And 3 minus -1, that's 3 plus 1 gives me 4. And then rewriting row 2. Now, at this point, I'm pretty much solved. I just want to scale. I'm going to scale row 1 and row 2 by 1/3. So I can get my result out. So when I scale the rows by 1/3, I'm going to get 1, 0 augmented with 4/3, and 0, 1 augmented with -1/3. And this is my vector x hat. Yes. With entries 4/3, -1/3. Okay. So we have the solution. We're also practicing using the inverse as well. I like to focus on the normal equations. That's what you can expect from me going forward. But let's see about solving directly, where x hat should be given by A transpose A's inverse times A transpose B. Gives us a way to solve directly. What was A transpose A? We remember that. Let's find the inverse. So A transpose A's inverse, it's going to be 1 over, and then the determinant of A transpose A, that's 6 times 42 minus 6 times 6. And then into the following rearrangement on the main diagonal, exchange those entries. Off the main diagonal, flip the sign. And now, with this, I would maybe just try to clean up this determinant a bit more, but I might not do too much scaling. I could do let's do some scaling maybe. Remember, 42 is 6 times 7. So this is 6 times 6 times 7 minus 6 times 6. And then if I got some room for it, this is the matrix that I'm multiplying this into. And I can factor out a 6 times 6. So that's 1 over 6 times 6. And then I'm left with, in parentheses, 7 minus 1. I have that 1 as a placeholder. And then into this. And now, actually, if I want to finish some of my arithmetic here, this is 7 minus 1 is a 6, so that's 1 over 6 times 6 times 6 into this matrix. And something that I would recommend doing, I can take one of these 6's in the denominator here and just bring that in, and that's going to clean this up, leaving me with integer still, and I'm still going to have some coefficient. That's something that I would do as a preference. I would say, well, hey, I don't want to maybe bring all of this in to do the division, because I think that's going to make things look like crazy fractions, and that's fine if you like crazy fractions. But if I want things to still look nice, but to cut this down a bit safely, I'm going to pick on one of the 1/6 and distribute it into the matrix. I'm going to multiply it into the matrix, right? Think about it like just affecting all the entries. So distribution is not quite the word I want to use, but you get the idea. 42 divided by 6 gives me 7, and then -1, -1, and 1. So I'm just picking on one of the 1/6, but I still have a couple of them hanging out in front. Now this is an expression for A transpose A's inverse, but then I can find x hat by doing A transpose A's inverse times A transpose B. And that's 1 over 6 times 6 times, I got this nice looking matrix now, and then A transpose B, what was that? That was here, that was 6 minus 6. And here's where something really nice is going to happen. I can now pick on another one of these 1/6, and I'm not going to bring it into the matrix, but since all of this is being multiplied, I'm going to bring this to affect the vector. It just gets better and better. You could also think about factoring a 6 out of the vector and then bringing it over here if you prefer that kind of approach. Same difference. But we're able to get rid of almost all of those coefficients, and now this is going to be, if I divide by 6 here, 1 minus 1. Real nice. I'm going to leave this in front. I'm going to worry about that later. I'm going to multiply now. So I still have the 1/6 weighting. If I multiply these together, I get 7 times 1 gives me 7, plus -1 times -1 gives me 1. -1 times 1 gives me -1, plus 1 times -1 gives me -1. So I'm going to get 1/6 times the vector 7 plus 1 is 8, -1 minus 1 is -2. And I can go ahead and bring that 1/6 in. So I get 8 over 6, and then minus 2 over 6. But then now we would say, hey, reduce this. Yeah. So here I can divide the top and the bottom by 2. It's going to give me 4/3. Here I can reduce by 2 as well. It gives me -1/3. And that is our vector x hat. So we found it another way, right? Using inverses. I really like those normal equations, solving the augmented system. We see it gives the same result too. We can use inverses where possible. Well, now let's take a look at a couple more examples. But in here, we're saying, in the following example, find the orthogonal projection of B onto the column space of A, and then to find the least square solution of AX equals B. So here I have this matrix A, and I have this column vector B, but I want to point out that A, and think about these as columns, as column vectors, column little a sub 1, little a sub 2. These as column vectors, think of them as vectors in a set, are orthogonal in this case. I get 1 times 5 plus 3 times 1 plus -2 times 4 when I do their dot product. The dot product is 5 plus 3 minus 8, or 8 minus 8, which gives me 0. So we'll say, hey, A1 dotted with A2 gives me 0. So this is a matrix with orthogonal columns, which means that if I want to build my projection B hat, I can do that. I can definitely do that. And how is that going to look? Well, it's going to be A sub 1 dotted with B over A sub 1 dotted with itself times vector A sub 1 plus A sub 2 dotted with B over A sub 2 dotted with itself times vector A sub 2. So here we can go ahead and build this as an orthogonal projection. So let's go ahead and see what that looks like. So if I do A sub 1 dotted with B, I'm going to get 1 times 4 gives me 4, 3 times -2 gives me -6, -2 times -3 gives me +6, over A sub 1 dotted with itself, 1 times 1 is 1, plus 3 times 3 gives me 9, plus -2 times -2 gives me 4. And then here, I can do this for the second piece. A sub 2 dotted with B is going to give me 5 times 4, which is 20. 1 times -2 is -2, and 4 times -3 is -12. Divided by A sub 2 dotted with itself, 5 times 5 is 25, plus 1 times 1 is 1, plus 4 times 4 is 16. And I do want to introduce those column vectors back in, but for now I'm just finding the coefficients. Let's see what it looks like. So -6 plus 6 gives me 0, so I have 4 over, this is going to give me 14 times vector A sub 1, plus, and then here, -2 minus 12 is -14, 20 minus 14 is going to give me 6, divided by here 25 plus 1 plus 16, so 25, 35, 40, 41, 42 looks like, times A sub 2. Here we can go ahead and reduce the top and the bottom of the first coefficient by 2. It's going to give me 2 over 7 A sub 1. And here I can reduce by 6. So that's 1 over 7 A sub 2. And now, hold on to this, because we're going to come back to this, but let's actually build this vector B hat. So this is equal to B hat. So that's 2/7 times vector A sub 1, the first column, plus 1/7 times vector A sub 2, the second column. What was A sub 1? Well, that was 1, 3, -2. And what was A sub 2? That was 5, 1, 4. Yes. Let's just go ahead and do the arithmetic here to find out what this gives us. So I get 2/7 plus 5/7 gives me 7/7, which is 1. Here I get 6/7 plus 1/7 is going to give me 7/7, which is 1. And here I get 2/7 times -2 is -4/7 plus 4/7 is going to give me 0. So this is what I get for my vector B hat. B hat, this orthogonal projection now, is the vector 1, 1, 0. But I still want to maybe know what x hat is. I want to know what x hat is because that's going to bring me from the column space of A to the projection. What is vector x hat? Well, it's lurking here somewhere in our work. Remember, it's a times x hat equals b hat. X hat must be the weights on the columns of A that bring us to vector b hat. So if you know what I'm talking about, the weights on the column vectors of A that bring me to vector b hat are these coefficients that we found. These coefficients that we found are important. This gives me vector x hat. The weights are 2/7 and 1/7. So it's hiding there in our work, definitely. We got this extra page here. You are amazing. The best students ever. If you're watching this video just on YouTube and you're not in my class or you're just here to hang out on the internet, you're amazing too. And you deserve, since you're not paying tuition, you deserve a smiley face. Think of that as paying tuition, kind of. Anyways, let's take a look at one more example and then we're going to get out of here. That's it. We'll take a look at this matrix A. Think of them as column vectors, A1, A2, and A3. And we have vector B. Now, I'm not going to go through showing that all of these are pairwise orthogonal, but they are. If you went to do A1.A2, A1.A3, A2.A3, all are going to be orthogonal. I have orthogonal columns to this matrix A, which means that I can build the orthogonal projection B hat. It's going to be A1 dotted with B over A1 dotted with A1 times column vector A1 plus A2 dotted with B over A2 dotted with A2 times column vector A2 plus A3 dotted with B over A3 dotted with itself times column vector A3. And let's find it. Let's do it. Make sure I have enough room for everything. I'll scroll down and do the other one later. Let's do this. I'm too excited. So A1 dotted with B, not a lot to it. 4 times 9 gives me 36, but the rest of that dot product is going to give me zeros. So 36, but then divided by A1 dotted by itself, 4 times 4 gives me 16. 1 times 1 gives me 1. 6 times 6 gives me 36. 1 times 1 gives me 1. Now A2 dotted with B, we get 0 times 9, negative 5 times 0, 1 times 0, negative 1 times 0, all of that is 0. But then divided by A2 dotted with itself, 0 times 0 is 0, negative 5 times negative 5 is 25, 1 times 1 is 1, negative 1 times negative 1 is 1. And then scrolling down here, because there's one more piece, I didn't forget about it. 1 times 9 gives me 9, and then the rest are going to be 0, right? But then divided by A3 dotted with itself, 1 times 1 is 1, and 1 times 1 is 1. 0 times 0 is 0. Negative 5 times negative 5 is 25. And let's clean up these coefficients, because you know they're important. I have 36 divided by, here I have 16 plus 36, so 40, then 52, plus 1 is 54, times a sub 1, plus, and this is 0 divided by 27 times a sub 2. And here I have 9 over 27 times a sub 3. And I can reduce these. 36 divided by 54. I know I can reduce by 9 on top and bottom. If I reduce by 9 on top and bottom, I'm going to get 4 over 6. But that's going to reduce even further, because now I can reduce by 2, it looks like. So I could have reduced by 18. So here if I reduce this even further, it's going to give me 2/3 a sub 1 plus 0 over 27 is 0, a sub 2. And then 9 over 27, I can reduce the top and the bottom by 9. So that's 1/3 a sub 3. And remember, this is going to be important. We're going to come back to this. But right now, I really want to build that projection vector b hat, where b hat is 2/3 times that column vector a sub 1 plus 0 times the column vector a sub 2 plus 1/3 times the column vector a sub 3. Let's find these vectors. A sub 1, that's 4161. A sub 2, 0, negative 5, 1, negative 1. A sub 3, that was 1, 1, 0, negative 5. Now, this middle computation, 0 times this vector a sub 2, is just going to give me the 0 vector. So I'm not even really thinking about that one too much, perhaps. But here, what do I have? I have 4 times 2/3 is going to give me 8/3, plus 0, plus 1/3. 2/3 times 1 gives me 2/3, plus 0, plus 1/3. Here, 2/3 times 6, I can reduce this. 6 divided by 3 is 2. 2 times 2 is 4. And then plus 0, and then plus 0. And then 2/3 times 1 is 2/3, plus 0, and then minus 5/3, it looks like. So what's this going to give me? Keep going with it. 8/3 plus 1/3 gives me 9/3. You know what to say about that. 2/3 plus 1/3 gives me 3/3. You got it. 4 plus 0 gives me 4. And then 2/3 minus 5/3 is negative 3/3. So let's just call it what it is. 9/3 is 3, 3/3 is 1, 4 is 4, negative 3/3 is negative 1. So this is my orthogonal projection vector b hat. But a really good follow-up question is, well, what about the vector x hat? Right? There is some vector x hat where a times x hat will bring me to that projection vector b hat, and we really want this x hat as part of our solution, definitely. I don't want to leave without it. Well, that should be the weights on the columns of matrix A that bring me to that projection vector, and we have that information right here. The weight on a sub 1, the weight on a sub 2, the weight on a sub 3. This is going to build the vector x hat, 2/3, 0, 1/3. This is our vector x hat. Hey, I hope you enjoyed this. Really fun talking about this stuff. No matter where you are and what you're doing, remember to always keep learning, keep dreaming, and to follow your heart. And I will see you next time. Until then, take care of yourself.